So, the question reads, the question of the moment reads, what does it read? The bond energy of ozone is 363 kilojoules per mole. Calculate the wavelength of UV radiation needed to break the bond. Clear? Okay. Now, okay. Let's get the equation first. So we need wavelength. Here are my two equations that we need. Right. We can substitute in for nu. We can substitute in what? Nu equals what? Sorry, nu equals C over lambda. Correct? Is that correct? So then we have E equals HC over lambda. Is that correct? Now we've got to solve for lambda. So we know that lambda is going to exchange these two things, right? You know that? Easy? Okay. Equals HC over the energy. And we need to do a mole of particles. Okay. We're going to do a mole. All right. So what is H? It's called Planck's constant. We've seen it before. What is it? What is it? It's right there. It's in your notes. What is it? Yes, Portia.
6.63.
6.63.
Times 10 to the power negative 34.
34. Okay, what are the unit labels? We should put unit labels in. You see the unit labels? What are they? Joule seconds, okay. Joule seconds. And then the speed of light, we use the meters, not centimeters. And that's going to be, anybody know that?
3 times 10 to the power 8.
3 times 10 to the 8th meters per second. Okay. And then what is the energy of the photon? What is the energy of the photon that we're going to use? Okay, it says 1 mole of photons are needed to break 1 mole of bonds, correct? The energy of a mole of photons is the energy of 1 photon multiplied by Avogadro's number, correct? Yes? We all right with that? So what's going to be the energy that we're going to need? What's the energy we're going to need? What's the energy that we're going to need? Anybody? Anybody? So we're going to divide it by, well, what energy do we need to break the bond? Don't we need this?
Yeah.
Right? But in joules, right? So it's going to be 363,000, right? Right? Per mole, right? So we're going to need 363 joules per mole. Correct? We'll say, should we say particles? Should we say particles? 6.02 times 10 to the 23rd. What? Bonds or particles? Right? Mole of ozone. We'll say particles. Okay? We'll say particles. And then what are we going to do?
Put the ozone in mole calculation.
What is it? Don't forget we want to calculate the wavelength of radiation needed to break the bond. So you see that I'm saying, well, all right, fair enough, I have that many bonds, correct? Yes. So I want to divide by this, so it's the same thing as multiplying by it's reciprocal, correct? So can I work over here? Is this on, is that on the film? Is that on, that box?
Yeah.
Is it? Okay. So it's going to be 6.63 times 10 to the negative 34. Let's leave off the unit labels because they all match. You know, in physics, when you're doing physics problems, as you may or may not have learned, you have physics, right? Munkel, do you have physics? No, you don't. That, as long as you're using like joules and meters and seconds and that sort of thing, then you're okay. Okay? So as long as that's the case, joules, seconds, meters, seconds, everything is cool. Okay? So we can leave off the unit labels. Okay? And it's going to be that times 3 times 10 to the 8th. And then it's going to be times the reciprocal of this, correct? Yes? So it's going to be 6.02 times 10 to the 23rd divided by 363,000. And what's that going to be? So multiply that out. Okay, multiply that out. Let's see how much room I have to work on over on the left. All right, so I can put in some extra stuff there. So my wavelength here is going to be equals wavelength. Okay? And then my lambda is going to be what? What is it going to be? What's the answer? Anybody? Do that out. What is it?
3.3
3.3
times 10 to the power negative 7.
times 10 to the negative?
Negative 7.
Negative 7. Okay? And what's the length going to be? If you've done the unit labels correctly, and we've done the unit labels correctly, what is the unit label for length?
Meter.
Meters. Okay? Is that really what they want? They don't really want that because you're not going to really find that. Why don't we look up on our computers? Do we have computers out, or you guys have your computers with you, or?
Yeah.
Okay, why don't your phones are fine, whatever. Look up the nanometer range of ultraviolet light right now. Okay? And then I'm going to show you. I'm going to erase all this, and then I'm going to show you. Okay? And we're going to talk about, well, all right, well, let's talk about, now we talked about the breaking down of the ozone, but what about the building up of the ozone? Okay? .3 times 10 to the negative 7th meters. Okay? That is the answer. Correct? Okay, now. While you're doing that, I'll convert this to nanometers. Okay, so you have 3.3 times 10 to the negative 7th. Okay, and then we want to multiply that by, get rid of meters, go to nanometers. Okay, in 1 meter, how many nanometers are there? Okay, meters is larger, so it gets a 1. It's just the way I do it. And then is it going to be 10 to the 8th, 10 to the 6th? How many nanometers in a meter? Do you guys know?
1,000?
A dozen?
1,000.
1,000? No. No. There are 1,000 millimeters in a meter.
It's 90.
A billion. 10 to the 9th. Right? Okay? So, what's this going to be? This is going to be 3.3 times 10 to the 2 nanometers. Correct? Yes? Do you see that? And that's simply going to be 330 nanometers. Okay? Now, what's the range? What's the range of ultraviolet light in nanometers? Anybody find it? Portia?
10 nanometer to 400.
Nanometers.
Yeah.
So tell me that again, 10 nanometers?
Yeah, to 400.
10 nanometers to
400.
400 nanometers. So that's the range of ultraviolet light?
Yeah.
So is that in the range? Yeah. Easy? Now how do you build up? How do you build up ozone? Anybody want to tell me that? Lauren?
You have to break O2 with the 242 nanometer wavelengths, and
Say that again, Lauren.
you have to break O2 with 242 nanometers, like wavelength.
So in order to do this, you got to break O2 down first.
Yeah.
And how are you breaking O2 down? Tell me that.
It needs, if a 242
So you're taking 242 nanometer
yeah, and
photons, right, of light,
yeah.
and you're breaking down O2, and then what are you doing?
Then the O2 is paired with the O3 the broken O2 has an electron and it's unpaired, so it's a free radical now.
And it's paired with another, it's a free radical,
Yeah.
I like that, and then it's paired with another O2
Yeah.
and as a single bond,
Yeah.
and that forms the ozone.
Yeah.
And then the ozone is further broken down back to its original thing by
But if it gets
the
another
330.
yeah,
Go ahead.
and if it gets another free radical oxygen atom, then it turns into 2O2.
Then it turns into two O2s. So you would need 4 of them, right, essentially?
Yeah.
Okay,
Because you would have
two O2s.
2 free radical oxygen atoms and 2 bonded oxygen, so you would have, yeah.
Excellent, excellent. I'm not sure everybody picked that up, but that was pretty good. That was pretty good, excellent. So an important for your studies, okay? Are we done? All right, very good.